In the interest of full disclosure, I'll say for the first 5 minutes or so of class this morning, I had the mic off, so I'm actually re-lecturing right now to an empty room, and then later on I'll pick up the lecture when the students were in the room. So up to this point, we talked about atomic structure. We talked about what's in the nucleus, where the electrons are around the nucleus, and so now we're going to talk about how that structure essentially leads to the properties that atoms have, and how different atoms of different elements have different properties because of that relationship. So hopefully you recall from your first chem class that valence electrons, the outermost electrons, are the most important ones. So when I say outermost electrons, what I mean is the ones that are in the highest energy level. And those are going to be the most important electrons because those are the electrons that bump into other atoms. And so when an atom is moving around, the inner electrons are really sheltered. They never really get out much. But the outermost electrons, the valence electrons, are the ones that bump into other atoms. So because they're the ones that confront the world, they're the ones that are going to determine what the properties of that atom are. So some things you should remember about valence electrons. The number of valence electrons in an atom can be found based on the column in the periodic table. So you want to be able to do that. For instance, nitrogen is in column 15, group 15 in the periodic table. It has 5 valence electrons. You can always go and do the full electron configuration if you want, but that's just going to confirm for you that you end up with that number of valence electrons. And so for the most part, we're not going to be doing complete electron configuration. For the most part, we focus on just the valence electrons. One thing you want to know is that the concept of valence electrons is not really useful for elements in the middle. So we only use it for the S and P blocks. And because we only use it for the S and P blocks, and because there's only 8 columns in the S and P blocks, the most valence electrons an atom can have is 8. Because once you filled up the S and the P on a certain energy level, you then go to a higher energy level before you fill up the D and the F. So the maximum number of valence electrons in an atom is 8. So we'll focus on valence electrons and what their relationship is to the nucleus. And specifically, what we're going to be concerned with is how tightly held are they. Okay, if they're not tightly held, then when they bump into another atom, maybe an electron jumps off. If electrons are really attracted to the nucleus, maybe when they bump into another atom, an extra electron jumps on. Or they may be able to share electrons. That's going to be based on how tightly held valence electrons are. So if we want to answer this question, we really need to remember the 2 factors that are going to affect the strength of the electrostatic force. First being the magnitude of charge, and the second being the distance between the charges. So for us, when we're considering magnitude of charge, essentially that's going to be the magnitude of the charge from the nucleus. The charge of a valence electron, charge of an electron, is always 1. So we're going to be considering, like, what is the magnitude of charge of the nucleus, but with one little wrinkle that we'll talk about in a minute, because the valence electrons don't feel the full charge of the nucleus. So really, this is going to come from the nucleus. An electron is always -1, but a nucleus could be +5, could be +10, could be +20. Then we have to consider some other effects. And then distance between charges really means between the nucleus and the valence electrons. All right, so at this point is where I turn my mic on in class, and so I'm going to now tack on the lecture from class from this point on. So let's think about how these two things change as you move around the periodic table. All right. First of all, if we want to consider the magnitude of the charge, why does the magnitude of the charge change? What is it that changes when you go from one element to another? The number of protons in the nucleus. So you might think magnitude of charge is just going to be about how many protons are there in the nucleus. And that's part of it. That's one factor to consider. But we also have what we call electron shielding. So you have protons in the nucleus, but then between those protons and the electrons on the outside, there's a bunch of other electrons. If you're an electron on the outside, how do you feel about other electrons? You're repelled by them. So when you look toward the nucleus and you're trying to feel that attraction to the nucleus, the electrons between you and the nucleus are repelling you, so they're counteracting the attraction of the nucleus. So the electrons between the outermost ones and the nucleus shield the outer ones. Okay? So valence electrons get shielded from the nucleus. By the inner electrons. They essentially cancel out some of the attractive effect of the nucleus. So it cancels out some of that attraction that they feel to the nucleus. All right. So to account for that, what we calculate or what we estimate is what we call the effective nuclear charge. It's what is the charge that the outermost electron feels after you consider the fact that there are electrons between it and the nucleus. So effective nuclear charge. Z is often used for the charge on the nucleus. So we're going to call this Z effective or ZEF. So effective nuclear charge is the charge, it's an estimate of the charge felt by the valence electrons after you consider the shielding effects of the inner electrons. To make life simple, the way we usually calculate it is just take the number of protons in the nucleus, that's the total positive charge, and then subtract the number of inner electrons. So we assume that for every inner electron, it cancels out the attraction of one proton. So it's roughly equal to the number of protons in the nucleus minus the number of inner electrons, or core electrons. That would apply to ions as well, yep. All right, so let's calculate a few Z effective values and see if we can see a trend. As we move from left to right, all right, so let's just take, say, lithium, beryllium, boron, and so on. Lithium has how many protons in its nucleus? 3. So lithium would have a 3 plus charge. And just to keep things simple, I'm just going to draw Bohr models for these things. How many inner electrons does lithium have? 2. And then it's got 1 outer electron. So if we're calculating Z effective there, we would say, all right, the charge of the nucleus is plus 3. And then there's how many shielding electrons? There's 2. There's 1 on the outside that's being shielded by 2. So if you're this valence electron in lithium, you feel like the nucleus has a plus 1 charge. You're looking at the nucleus. What you see is something with a plus 1 charge. Beryllium has how many protons in its nucleus? 4. Again, has 2 core electrons and 2 valence electrons. So we've added a proton. We also added an electron. The electron we added went to the same outer energy level. Since those 2 on the outside are on the same energy level, they don't really shield each other as effectively. So we're essentially going to ignore their shielding effect. So the effective nuclear charge in this case would be plus 4 minus the two inner electrons. So now plus 2. So the question is, we just don't count the valence electrons. Right, we don't count the valence electrons as shielding each other because they're not between each other in the nucleus, essentially. The reason the core electrons are shielding is because they're between you and the nucleus. So you can't, if you're a valence electrons, you essentially can't see past them. It's sort of like there's someone you're really attracted to, but they're surrounded by people you really don't like. It kind of takes away from your desire to be near them. If they're attractive enough, they can overcome that shielding effect of those other people you can't stand to be near. But there's still a shielding effect there. All right. Boron. How many protons? 5. Still 2 1s electrons. And now how many valence electrons? 3. The effective is going to be now 5 minus, still 2 core electrons. So now plus 3. And we don't even need to do carbon. we can see the trend. So as you move left to right in the periodic table, oh, I left myself a whole new slide. I'll write on the new slide. As we move to the right, we add more protons to the nucleus. But we add more electrons to the valence energy level. We don't add any more core electrons. So there's no extra shielding. So what happens to Z effective? Z effective increases. Yeah. Turns out Zeph is equal to the number of valence electrons, unless you're looking at an ion. Yep. So good observation. So if you want to know Z effective for a neutral atom, yeah, it's just going to be equal to whatever the number of valence electrons is. So lithium had 1 valence electron, Zeph was +1. Beryllium had 2 valence electrons, Zeph was +2. But I would not say, for instance, you're trying to explain a trend in how strongly attracted the valence electrons are. I would not say, okay, as you move from left to right, the valence electrons are more attracted to the nucleus because there are more valence electrons. Why would that be a faulty argument? To say that moving from left to right, the electrons are more attracted to the nucleus because there are more valence electrons. Okay. Because electrons do what to each other? They cancel out the effect of the nucleus, they repel each other. So it's a faulty argument. It doesn't make sense to say the electrons are more attracted because there are more valence electrons. The fact that there are more electrons actually makes electrons less attractive. So really, to explain the trend going left to right, you have to talk in terms of the number of protons in the nucleus. Because you're adding more protons to the nucleus, but you're not shielding those extra protons, you're increasing the effective nuclear charge. So charge increases as you go from left to right. How about distance? Our simplest estimate of distance comes from what energy level the valence electrons are on. So if Zeph is increasing, but the valence electrons are on the same energy level, their distance is going to remain roughly the same. It turns out their distance actually gets a little shorter. They do get pulled in closer to the nucleus. But same energy level means distance doesn't drastically change. Or it definitely doesn't get any bigger. So you have greater charge, same distance. From left to right in the periodic table, that tells you greater charge, same distance, stronger force of attraction. So if you want to explain the trend going left to right in the periodic table, that's how you can do it. Any questions? All right, so what if we're going top to bottom in the periodic table? So now let's take, say, lithium, and then we'll consider sodium. Lithium, we already said, there's 2 core electrons, 1 valence electron. And Zeph was +1. All right, if I'm going to model sodium, how many protons in sodium? How many? 11. All right. I'm going to need to give myself more space. So then we have 2 electrons in energy level 1. How many electrons in energy level 2? 8 total. 6 in the 2p, 2 in the 2s. 1, 2, 3, 4, 5, 6, 7, 8. And then I've got my 1 valence electron sitting out here. And while there are 11 protons attracting it towards the nucleus, there's this whole like phalanx of blockers there, canceling that out. So Z effective for sodium would be 11 protons minus how many core electrons? 10. So from top to bottom, what happens to Z effective? Stays the same. All right. So the effective charge is staying the same, but what's happening is the distance is increasing because we're moving to higher and higher energy levels. As you go down the periodic table. So that means distance increases. So if you have same charge of attraction, greater distance, we said, what happens to the force? It gets weaker. Yeah. So we have a left to right trend and a top to bottom trend, and they essentially go in opposite directions. All right, so to summarize that, we have 2 factors to consider, number of protons and valence energy level. And just based on knowing that, we were able to reason out why electrons would be more attracted to one atom than another. Higher energy levels further from the nucleus, so electrons not held as tightly. Greater distances, weaker force. More protons in the nucleus lead to a greater attraction. And the inner electrons shield the outer ones, so really we have to consider the effective nuclear charge. So to summarize that, if we're considering pull on the outermost electrons, as we go down the periodic table, when I think in your printout, this is embarrassing, I think in your printout there might be an extra column over on the right-hand side. Yeah, in the P block. So in your printout, cross out these 2. I know probably most of you wouldn't have noticed, but still, it bothered me when I caught it. So I feel the need to point it out. All right. As we go left to right in the periodic table, we said we have increasing Z effective, but we have same valence energy level. So what happens to the strength of the pulling force? All right, stronger pull. As we go down the periodic table, what's happening to Z effective? Constant. And what happens to valence energy level? As you go down, what happens to valence energy level? What is it? You're going to higher valence energy level. Yep. So the net result is you get a weaker pull. Yeah, weaker. You know, the pull from the force of attraction, essentially. Between the nucleus and the valence electrons. All right, so what we just did is essentially explain all of the way atoms behave just based on understanding Coulomb's law and knowing a little bit about the way electrons are arranged based on quantum mechanics. All right. So if you want to explain periodic trends at a fundamental level, this is how to do it. You may have, learned other shortcuts or things that are like magic, like saying things want to have a full valence energy level, and therefore there's a stronger pull when they get closer to having a full valence energy level. That's not a good argument. It's actually a backward argument. So in this class, when you're trying to explain things, I want you to refer to fundamental physical principles, because it's not that complicated to do that. And they will not fail you. Some of these other magic things, you may have learned that a half-filled energy level is especially stable. Forget that. It's not true. It's just calling on magic. All right. So there's our fundamental explanation. So the question is it a myth that they want full energy level? I would say a more accurate statement is, in stable chemical compounds, atoms tend to end up with full valence energy level. But it is a myth to say an atom always wants a full valence energy level and will do anything to get it. So for example, if you take oxygen and you give it one electron, it'll get happy. Most atoms like to accept one electron. They're like, all right, one electron. I love this. This is great. And then it'll be O minus 1. So now it would have 7 valence electrons. If you try to give oxygen another valence electron in a vacuum and make it O2 minus and give it a full valence energy level, it'll say, no, thank you. You actually have to put in energy to make it take an extra electron. So that's an unfavorable process. And if you're thinking just in terms of, well, it wants to fill up its valence energy level, then, there's no way to account for that fact. So the picture is a little more complicated than things just want to have a full valence energy level. We will use that octet rule a lot as a rule of thumb. It's helpful to come up with the structures of compounds, etc. But it's not a fundamental thing, and generally we can break it down and explain it on a simpler level like this. All right. So that's our general principle, and then what we'll do tomorrow is just extend this to some specifics. So we'll talk about specific properties like, well, what is electronegativity or ionization energy? How big is the atom? Is it going to be metallic or non-metallic? And what do those two things mean? So tomorrow we'll just take this and apply it to specifics.